Welcome to lesson number 1 on waves from the light and sound section. We are now on to lesson 1, part 3, which is the wave equation. This is so important. The wave equation, you're going to be asked this 2 or 3 times in your exam in June because they ask it every single year. It's one of the most important equations in physics. So make sure you have your notes downloaded so you can do the class along with me. So we're on to 1.3, which is the wave equation. So let me explain it like this. So you know that oscillators make waves. So this represents the surface molecules of water. At the moment, they're dead calm. But then an oscillator comes along. You might be dropping a stone into a pond, or your hand might be moving up and down in the water. And as a result of that, you're going to disturb those water molecules. Those water molecules are going to start moving up and down. And because they're attracted to each other, well, they're going to cause ones beside them to move up and down. And so the wave travels out through the water. The disturbance is traveling in this direction. This is the direction of the wave. Whereas the individual particles, you can see, are moving up and down. Their movement is at right angles or perpendicular to the direction of the wave. That's actually an example of a transverse wave, but more about that in the next part of this lesson. Now let's say I freeze the wave. So it's suddenly frozen. This is what the wave now looks like. The speed at which the wave moves to the right is called its velocity or speed v. V actually depends on the medium through which it travels. So, for example, if it's traveling through water, it's going to travel at a certain speed. But if it travels through oil, which is a lot more viscous, stickier, then it's going to travel more slowly. The speed depends on the medium through which it travels. You know this already. The high point in a wave is called the crest. And the low point in a wave is called the trough. What's one full wave? You know from the previous part of the lesson what one full wave is. Starting here, I go up, and then I go down, and I come back to my starting position. So that there represents one full wave. Along the x-axis, I've got the distance s it's traveling. Along the y-axis, I've got the displacement through which these particles are going up and down. And you know what the maximum displacement is? The maximum displacement will be the high point in the wave. So that high point in the wave, that's called A, the amplitude. We're now going to do a very important definition called the wavelength of the wave. What's the wavelength? The wavelength will be the distance a full wave travels. So it starts there and it finishes there. So this distance here, it's gone from start to finish. That distance there, that represents the wavelength. And I'm going to represent the wavelength by a Greek letter. And the Greek letter is lambda. I want you to be able to say lambda. I'm going to write it down. I don't want you to say things like that squiggly thing. I want you to say your Greek letters properly. So there it is, lambda. So lambda is the distance a full wave travels. But actually, we can say it in a different way. We can say that the wavelength is the distance from one crest to the next crest. We call that successive crests. You can also say from one trough to another trough if you want to as well. That there is also the wavelength. And why is that the case? Well, is that the same length as a full wave here on the left? It would be. Here's the start of it. That's a quarter of a wave. There's a half a wave. And here's the finish of it. There's a quarter of a wave. So they add up all together to give you a full wave. So actually the definition of wavelength will be the distance from crest to crest. Now, I want you to be able to derive the wave equation. You won't necessarily have to do this for the leading cert, but I think it's good practice. You know, if I can show you where something came from, you're going to be a better physicist, a much better physicist. So I'm going to prove it for you. Velocity, V, in general, you know from your junior cert, is distance traveled. I'm calling distance S, divided by time, the time it takes to travel that distance. Now, the speed of that wave is constant throughout. So let me take a certain distance and the time it takes to travel that distance. Well, why don't I take one full wave? How far does it travel in one full wave? Obviously, it travels what's called the wavelength. So the distance is lambda. And then how long does it take to travel that full wavelength? We did this in the previous part of the lesson. It takes the periodic time. The periodic time is the time for one complete cycle. So T, periodic time, we call capital T. Now I'm going to use a formula that we had from before. You know that the frequency F is equal to 1 over the periodic time. You see, I've got 1 over T there. If I replace 1 over T by F, I'm going to get F times lambda. And that there is my wave equation. V is equal to F lambda. You need to know what everything stands for. Well, V stands for the speed or the velocity of the wave. What are its units? The units for speed you know already. Distance, meters, divided by time, seconds. That gives me meters per second. F stands for the frequency. The units for frequency are hertz. And finally, lambda is your wavelength. And you know what? That's just a length or a distance. So it's going to be measured in meters. Right, let's go back to our notes. So there's the formula that we just derived, the wave equation, V is equal to F lambda. Do you know, in the table book, it actually appears in a slightly different way. It appears as C is equal to F lambda. Why is that? Well, C is a very famous speed. It's the speed of light, and nothing can travel faster than the speed of light. Personally, I prefer to use V is equal to F lambda when I'm dealing with sound waves and water waves. And I will deal with C is equal to F lambda when I'm using light. But in your table book, just be careful. So if we look at our table book, we're going to underline this. This is on page 59. And there's the velocity of the wave formula. C is equal to F lambda. But you can equally write down V is equal to F lambda. What about definitions? Well, here's your definition for wavelength, lambda. There's no star beside it, no asterisk beside it. So just basically learn it. The wavelength lambda is the distance between two successive crests in a wave. And we also have the definition for the velocity v of a wave. That's the speed at which it moves through a medium or a vacuum. So learn those two definitions. Let's move on to example 2. So in example 2, an oscillator makes a complete cycle in 0.2 seconds. You know what that is, don't you? That there is the periodic time. The oscillator produces waves which travel through a material medium at 10 meters per second. That's the velocity of the wave. The amplitude of the waves, that's the maximum displacement in either direction, is 0.5 meters. So they're asking me to calculate the frequency and wavelength of the waves. Well, let's write down the information that I have so far. What do I have? I know that the periodic time t is equal to 0.2 seconds. I know that the velocity v is 10 meters per second. And I know that the amplitude, which I call a, is equal to 0.5 meters. And what are they asking me to calculate? They're asking me to calculate frequency, f, and the wavelength, lambda. Well, we're going to use our formulae. So I know what f is equal to. The formula for f is 1 over t. The periodic time, so it's 1 over 0.2. Put that into your calculator, or do it in your head. We get an answer of 5. And what are the units? The units, of course, are 5 hertz. Next, I want to work out the velocity. So I'm going to use my velocity formula. V is equal to f lambda. I'm looking for lambda. So write that formula in terms of lambda. Lambda's slide the f downward to the v. V over f. The velocity given is 10 meters per second. The frequency we just worked out to be 5 hertz. And the answer will give me 2 meters as the wavelength. And now, finally, they're asking me to sketch a graph. So they've laid the graph out for me already. We have displacement on the y-axis, and we have distance traveled there on the x-axis. Well, can I draw my graph from that? I can. So I know the highest my graph goes up to 0.5 meters in either direction. I also know this. I know that the wavelength is 2 meters. That means a full wave. Full wave will start there and finish at 2 meters. So this is how it goes. Here's my full wave. It goes up to 0.5. There's my half a wave, down to minus 0.5. And there's my full wave. There's enough room to put in another half a wave if you wish. There's a sketch of my curve. Let's move on to example 3. So you have a boy under a bridge, shouts, and here's his echo 1.8 seconds later. How far is he from the reflecting wall on the bridge? They give you the speed of sound in air to be 340 meters per second. They'll give you constants that are not in the table book. Like not every constant will be in the table book. So if it's not in the table book, they have to give you that constant. And speed of sound is not in the table book. Now, what I'm going to use here is just your general formula for velocity or speed. I'm going to use the formula velocity, v, is equal to distance divided by time. You're asked to find the distance the boy is from the bridge. We call that distance there S. So the boy shouts. So a sound wave is going to go out towards the bridge. So here's his voice going this way. It's going to hit the bridge. It's going to rebound and come back to him as an echo. The total time is 1.8 seconds. The time to go in one direction will be half, and back the other way will be half of the 1.8. In other words, the time will be 0.9 seconds. And we know we were given the speed of sound v, and that's 340 meters per second. So use your general formula for velocity or speed. I want to manipulate that to write it in terms of s. Slide the t up to the v, so I get s is equal to v by t. So put my numbers in. Velocity is 340. Time is 0.9 of a second. I'm going to put that into my calculator. 340 multiplied by 0.9. Always have your calculator out during these classes. Be an active learner. Don't just be watching me doing it. And I get 306 meters. Let's move on to example 4. It says visible light has wavelengths ranging from 370 nanometers to 700 nanometers. What is the frequency range of visible light? Okay, we're looking at something. That is a little bit different here. That nano, that little n thing, that's called a prefix, and that represents a power of 10. Now, you need to use your table book to find out exactly what power of 10 that prefix is referring to. If I go to my table book, page 45 is a very important page. And on page 45, you've got a list of all your prefixes. On the left-hand table here, we have all the big prefixes. On the right-hand table, we have all the smaller, tiny prefixes. I'm looking for nano. The nano is here, little n. And that represents 10 to the power of minus 9. So become aware of page 45. It's going to be very important in your exam. Let me talk briefly about prefixes before I do that question. We're talking about n is equal to nano. And that is equal to 10 to the power of minus 9. So in the example, for example, we have 370 nanometers is the wavelength. So I can write down lambda is equal to 370 nanometers. Well, the first thing you've got to do is make sure that you get rid of the nano. So replace nano by its power of 10, 370 by 10 to the power of minus 9 meters. You've got to do that with all the numbers that are prefixes. Now, that's not a pure number in scientific notation. Pure scientific notation would mean that number is between 1 and 10. If I put that into my calculator and pressed equals, it would give me 3.7 by 10 to the power of minus 7 meters. So that's that number written properly. You don't have to, by the way. You can put that into your calculator and do your calculation and you'll be fine. But that is pure scientific notation there. So let's go back now to example 4. So we're told the wavelength is 370 nanometers, lambda, and that's equal to 3.7 by 10 to the power of minus 7 meters. So they want to know the corresponding frequency for that. Well, we're talking about light now. So for light, I can use the formula C is equal to F lambda. Now, that value of c, the speed of light, that is in the table book. It's on pages 46 and 47. This is where all your constants exist. I'd actually suggest to you that when you're in the exam, that you always have those pages open, 46 and 47. They're the ones that you're going to be using most often. Where do I find it? I find it here. It's called the speed of light in vacuo. That means in a vacuum. And its value is given as that value there, 2.99792,458 multiplied by 10 to the power of 8 meters per second. Now, I don't want you to write down the full number. I want you to round it off to 1 or 2 decimal places. Here, that number will round off to 3 by 10 to the power of 8. So I'm going to write down the speed of light, c, is 3 by 10 to the power of 8 meters per second. Now I'm looking for the frequency of light corresponding to that wavelength. So I'm going to write the formula down in terms of F. So F is equal to c divided by lambda. Speed of light, 3 by 10 to the power of 8, divided by lambda, 3.7 by 10 to the power of minus 7 meters. So put that into my calculator. Fraction button. 3 by 10 to the power of x, 8, divided by 3.7 by 10 to the power of x minus 7. And that is equal to, 1 decimal place is fine, 8.1 by 10 to the power of 14. And of course, the units of frequency are hertz. Now, what about the other end? The other end, we're talking about We're talking about 700 nanometers. So lambda is equal to 700 nanometers. Once again, look up your nano and you'll get 10 to the power of minus 9. That's 700 by 10 to the power of minus 9 meters. You can use that number if you wish, as I said, but in pure scientific notation, your calculator will give it to you 7 by 10 to the power of minus 7 meters. The speed of light, 3 by 10 to the power of 8. F is c over lambda. 3 by 10 to the power of 8 divided by lambda, which is 7 by 10 to the power of minus 7 meters. So put that into my calculator. Press the fraction button. 3 by 10 to the power of 8 divided by 7 by 10 to the power of minus 7. And that's equal to 1 decimal place, say 4.3 by 10 to the power of 14 hertz. So that's the frequency range of visible light. So I suppose you're talking about starting from red light. Red light has a longer wavelength. That's one end of the spectrum. It's got a long wavelength and a short frequency. All the way down to the other end. The other end would be violet. I'm going to use blue for violet. It's got a smaller wavelength. You can see it's 370 nanometers, but it's got a higher frequency. So your answer will be, the frequency range of visible light will be from 4.3 by 10 to the power of 14 hertz up to 8.1 by 10 to the power of 14 hertz. Okay, so that's the end of the lesson. There's one more part of this lesson, but it won't contain any numerical problems. You're now in a position now to do the numerical problems. At the end of that particular chapter, you have a number of numerical problems which you should do. You've just got a number of simple formulae. What are they? Velocity is distance over time. Wave equation, velocity is equal to f by lambda. Frequency is 1 over time. Just getting used to them. Doing some simple problems that make you think. You've got 15 questions there with the answers given. Okay, so well done. That's the end of the lesson. Thank you very much.